Namaskar and welcome to this third lecture in this course on hydration, porosity and strength of cementitious materials, with the title of this lecture being Basic Properties of Concrete. The properties of concrete, both in its fresh state and the hardened form, are discussed in this lecture. Various fresh properties of concrete like workability, air content, setting time are explained with an emphasis on the testing methods, and properties of hardened concrete are then discussed in the framework of the three-phase model that we talked about in the last class, and we take examples from durability studies in concrete. We must keep at the back of our mind that even though we are going through concrete properties in this lecture, but that has to be in the framework that it facilitates understanding of cement and cementitious material hydration in the paste, which is an integral part of properties of concrete. So the topics that we will talk about today are the properties of fresh concrete and the properties of hardened concrete from the point of view of strength and durability. Now, when we talk of basic properties of concrete, we saw that we can look upon that as the properties of fresh state, where we expect the concrete to behave like a fluid, and in the hardened state, where we expect the concrete to behave much like a rock, which has taken the shape of the formwork. Now, how do we characterize the concrete in the fresh state and the hardened state is the discussion of the properties. So, in the fresh state, the properties that are of relevance and importance to us are workability, air content, temperature and temperature rise, setting and bleeding. In the hardened form, we can talk of properties which could be related to strength and the durability of concrete. Now let's look at some of these properties one by one. Workability is basically the ease of being able to work concrete into different parts of the formwork. Essentially, that means that a concrete will be deemed to have a high workability if it is easier for the concrete to fill all the spaces in the formwork. In the extreme case, a concrete that behaves like a liquid is very highly workable. This workability, the most commonly used test having a wide range of application is the slump cone test. That is shown here. It is a cone having 10 centimeters at the top, 20 centimeters at the bottom at 30 centimeters height. Fill this cone with concrete and lift the cone and wait and watch as the concrete slumps. So in this picture here, the extent of slump that we find is very small compared to this, and therefore the concrete in this picture, which is A, is stiff concrete, is not a very workable concrete. In picture B, we find what we can call a normal concrete. Whereas in picture C, we find that upon lifting this slump cone, the concrete cone has actually totally collapsed and has spread into more or less a circle. And that is what is a highly workable concrete. Where do we use these concretes? This stiff concrete finds application in places like road construction, where there is not so much of an obstruction for the concrete to move. On the other extreme, a highly workable or a fluid consistency concrete is used in placing with structures having extremely dense reinforcement or in situations where compaction is otherwise not possible. Other than the slump, there are other methods which are available to measure the workability of concrete, one of them being the compaction factor test, the VB test, and the flow table test. As an assignment, I would like you to read about these tests and the standard methods that have been prescribed in different standards of the world as to how these tests should exactly be carried out. Now let's come to air content. Air in fresh concrete exists in two forms. One is entrapped air and the other is entrained air. As this classification suggests, entrained air is one that is intentionally put in the concrete because that suits our purpose. It helps to enhance the performance of that concrete, whereas entrapped air is unintentionally present in the concrete and we seek to remove that to the extent possible through compaction and so on. The properties that the air content influences are workability. If we have more air content, the concrete becomes more workable because of basically the ball bearing action of air particles that facilitates the movement of particles one over the other. It reduces the friction between particles. However, increased air content also has the danger of contributing to reduced strength because at the end of it, air content is basically voids and we do not want the air content to reach levels where those voids become a source of introducing a problem as far as strength of the concrete is concerned. Air content is prescribed in concretes which are used in environments with cyclic freezing and thawing. Air content in concrete is determined using a pressure meter, and the usual ranges of air content in non-air entrained concrete, that is those concretes which have only entrapped air, is about 1 to 2% by volume, whereas in air entrained concrete, where we use chemical admixtures to entrain the air, the percentage could be between 4 and 6. Now let's talk about temperature. We must remember that hydration of cement is an exothermic reaction, and depending upon the balance of the heat generated within the concrete and the heat dissipated from that concrete because of the atmosphere, there could be a substantial rise of temperature in the concrete. The initial temperature of placement is an important factor that determines the maximum temperature reached during hydration, and at times efforts such as pre-cooling, the constituent materials, use of chilled water, etc. are resorted to keep the temperature of fresh concrete and the temperature rise in check. As far as tools are concerned, we use a simple thermometer to know or to determine the temperature of fresh concrete. Here is an experiment. Here is data that was collected in the lab using a simple experiment where a block of concrete was cast and the temperature at different locations in the block was measured, and you can see that starting with a temperature of about 29-30 degrees centigrade, the peak temperature reached was 63 degrees, and this happened at about 17.5 hours. In fact, it took practically 4 days, 96 hours, for all these sensors that are shown here to record atmospheric temperatures. So this graph shows how the temperature of concrete actually changes over a period of time, and there could be applications where a client or where it would be demanded that this peak temperature be brought down, or this peak occurring at a certain point of time be delayed. Now, these are the kind of things to address which we need to understand hydration, the rates of hydration, the effect of having mineral admixtures in the system more clearly. And that is where this course is headed towards. So, well, this is just a summary of what we just said. The temperature at the center was relatively high. The peak temperature about 63 degrees reached in about 17 hours. Setting of concrete is also an important phenomenon, and we must quantitatively determine the time of setting in concrete. We must remember that the setting time of concrete is not the same as that of cement. Cement setting time is a measure of the quality control of the cement. Those tests are carried out under standard and controlled laboratory conditions, whereas the setting of concrete in an actual site happens in the uncontrolled atmosphere. Also, when we are trying to determine the setting time of cement, we are working only with cement paste, whereas a concrete is not only cement paste but also has sand and coarse aggregate. So, indeed, there is reason to believe that if the setting time of cement is high or low, the setting time of concrete will also be high or low. But as far as quantitative treatment is concerned, it is not fair at all to say that we will translate the setting times determined in the lab for cement to be the setting time of concrete in the site. Now, therefore, we need an apparatus to determine the setting time of concrete, and here is this apparatus which is called the penetrometer apparatus, which can be used to determine the penetration resistance, which increases as the setting progresses. So, indeed, as the hydration progresses in the cement, the concrete sets, the penetration resistance increases, and after a point in time, it is no longer a matter of penetration resistance, but we get into a strength development regime. The needle of this apparatus is lowered gradually, and the penetration resistance to obtain a certain length of penetration is recorded. Now, here is this penetration resistance, which is recorded in MPa, which is plotted over a period of time, and as can be expected that initially the penetration resistance values are low and finally they become fairly high. So, arbitrarily standards suggest a certain value here to be taken as the initial setting time of concrete, and similarly the final setting time of concrete. As far as the Indian standards 8142 is concerned, this penetration resistance values have been taken to be 3.43 and 26.97 newtons per millimeter square, and I am leaving it to you as a small assignment to find out the genesis of these very odd looking numbers. We will probably address this question later on. Why do we need this assessment? We need an assessment of the setting time of concrete to better understand and better treat subjects such as cold joints, design of formwork, concreting rates, and so on. Now, let us look at bleeding. Bleeding is essentially the movement of water present in concrete towards the top after placing. We must remember that as far as concrete is concerned, all the constituent materials are heavier than water, and therefore no wonder that when they are mixed with water, at the end of it they try to settle down. In other words, water collects at the top as a result of this segregation that happens between the materials, and that is precisely what is bleeding. We need to quantify bleeding because this water that collects at the top, some of it evaporates, but some of it is absorbed back and results in a higher water cement ratio in the top layer. If the water that collects at the top of concrete, on the surface of the concrete, is removed and we try to plot this accumulated bleeding water with time, we will get a graph which is something like this, that initially we have very little water that comes, a large amount of water comes here, and finally no more water comes out, and then we get a cap or the limit of the accumulated bleeding water. And this amount of water that we get in relation to the water present in the concrete, this can be expressed as a percentage, and we can talk in terms of percentage bleeding. Now coming to properties of hardened concrete, we have strength. Indeed, strength could be compressive strength, but concrete is not all the time, in all applications, subjected only to compressive stresses, and therefore we often talk of the tensile strength of concrete or the flexural strength of concrete, and we use different kinds of specimens which could be cubes or cylinders to determine the compressive strength. We often use cylinders for the splitting strength and prisms to determine the modulus of rupture to get an idea of the tensile strength, and for flexural strength as well we use prisms. Usually these tests are carried out at 28 days or 7 days, as the case may be, depending on the application that we have. More importantly for us, we would like to understand the implications and the relationship of durability of concrete to the hydration process, and how do we try to control or better understand the durability characteristics of hardened concrete. So for that, let's take some examples of deterioration mechanisms, or what are the common deterioration mechanisms that we have in concrete. One of them is chloride penetration, and chloride penetration is important from the point of view that it leads to reinforcement corrosion, and reinforcement corrosion is an absolutely undesirable phenomenon as far as reinforced concrete or pre-stressed concrete structures are concerned. And the chlorides that move into the concrete structures the way that's shown here and cause the corrosion of this reinforcing bar is a matter of concern to us. Therefore, we need to have ways and means of finding out the chloride permeability of this concrete. As I said in the first class, strength, durability and porosity are all interrelated, and therefore the traditional wisdom of saying that if we have a concrete here which is stronger, then the chloride permeability will be lower. That is absolutely true, except that from a functional point of view or from the point of view of performance evaluation, it is always better to directly get information about chloride permeability rather than measuring strength and hoping that it is somehow related to chloride permeability. So we need tests for chloride permeability of concrete. Similarly, this picture here is that of alkali aggregate reaction in concrete. Now this is another undesirable situation. We would expect and like the aggregates in the concrete to be inert. Now in certain cases they are not inert, they are reactive aggregates, and therefore we can either simply not use reactive aggregates or try to understand the level of reactivity of those aggregates so that necessary measures can be taken to mitigate the damage on account of alkali aggregate reaction. The third picture here is that of concrete deterioration on account of freezing and thawing. So therefore, in environments such as this, where concrete is likely to be subjected to cyclic freezing and thawing, we would like to put in place a concrete which has a higher durability in that environment, for which we need to understand the durability characteristics of concrete in freezing and thawing environment. So in the subsequent slides, we will talk about tests which are available to quantitatively assess the chloride penetration resistance or the alkali aggregate reactivity or the resistance to freezing and thawing of concrete. This is only one of the tests which is used to ascertain the chloride permeability of concrete and is the so-called rapid chloride permeability test, which essentially involves placing a disc of concrete here in the middle. On two sides you have chambers which are filled with 3% NaCl solution and 0.3 NaOH solution, and we apply a 60 volt potential difference across the two faces, and we monitor the current that flows from one face to the other, and this recording is continued over a period of 6 hours, and we measure the total charge that passes, which is an integration of the current and time. And here is the interpretation that is to be given in terms of the coulombs, and that is according to ASTM 1202. If the coulombs is greater than 4000, the chloride diffusivity is rated as high, and if it is less than 100, it is rated as negligible, with other values being evaluated the way it is shown here. Of course, this is not the only test to determine the chloride permeability of concrete, but this is one of the tests, and as an assignment, I would like you to read literature and make a list of the other tests which are available to evaluate the concrete from the point of view of chloride permeability. Now let's come to alkali aggregate reaction. The real problem basically is that the aggregates are reactive and they react with the alkali in the concrete. Now where is the alkali in the concrete coming from? The alkali in the concrete refers to the presence of sodium and potassium ions, and these are coming in cement. These are impurities that are present in the cement as Na2O and K2O. So if you look at the chemical composition of cement, you will find a certain amount of sodium oxide and a certain amount of potassium oxide present there. There are ways and means of expressing the equivalent alkali content of the cement, and these alkali ions, they react with the reactive aggregates to form a reaction product, and this reaction product, upon absorption of water, it absorbs water, and this has an expansive nature and causes the concrete to crack. And depending on the classification that we have, if you read enough literature, you will find that people have tried to talk of alkali aggregate reaction into different forms: alkali silica reaction, alkali silicate reaction, and alkali carbonate reaction. What we basically need in order to study alkali aggregate reaction is the reactive aggregates. Sufficient alkali should be there to have a reaction with the aggregates, and there should be sufficient moisture, which will cause the expansion to happen, because these reactive aggregates and alkali, they form a reaction product which absorbs water to cause expansion. What are the results of this alkali aggregate reaction? Map cracking, strength reduction, and poor water tightness. How do we evaluate it? We do this evaluation based on tests such as the mortar bar expansion test, and this test is carried out using mortar bars cast using cement of known alkali content, sand conforming to a given particle size distribution obtained by crushing the rock sample under study, proportion the mix appropriately, and adjust the total amount of alkali that is present in the system by adding crystals of sodium hydroxide, cure the specimens, and measure the length. Now this here is a typical example of how the length changes, how much expansion occurs over a period of time if the aggregates are reactive. Of course, depending on our application, we can fix a line here which will separate the potentially reactive aggregates and the innocuous aggregates. And as in the case of the chloride permeability, this is not the only test to determine the alkali aggregate reactivity. And again, as an assignment, please go through literature and the books to find out what are the other tests and how do we interpret those results. Now coming to freezing and thawing, if the free water present in fresh concrete freezes, frost damage may occur to concrete as there is no sufficient space to accommodate the additional solids produced. Fully hardened concrete can also be subjected to severe frost damage due to alternate freezing and thawing. We must remember that we add more water to concrete than is required for hydration. Now, if this water remains in the concrete and the concrete is subjected to freezing and thawing, that is the free water that we are talking about. The water which is free and has not been used in the hydration process. Apart from that, in certain applications, the concrete absorbs water. If the structure is subjected to rain, for example, or it is subjected to any kind of water, it could be a river, it could be a sea, whatever it is, the pores in the concrete are saturated to different levels. And if that water freezes, it expands. And that cyclic phenomenon, if the water expands and it thaws, that causes deterioration and disintegration of the pores in concrete, and that is the genesis of the deterioration in concrete on account of freezing and thawing. Use of air entraining agents has been found to be a very effective way of creating a durable concrete from the point of view of freezing and thawing. Now, how do we evaluate the durability of a concrete from the point of view of freezing and thawing? That is done by the so-called relative dynamic modulus of elasticity of concrete. The test is carried out using the relative dynamic modulus of elasticity of concrete, and as per ASTM C666, there is a procedure given, there is an equipment which I would like you to read from the web or the books, and there is something called the durability factor, which we finally calculate. And as far as the durability of concrete to freezing and thawing is concerned, we evaluate it based on the durability factor. Now, if we plot the durability factor versus air content, we get a graph which is typically like this. What this graph shows is that if the air content in the concrete is less than about 3 to 4%, the durability factor is pretty close to 0. That means the concrete is very highly vulnerable to freezing and thawing damage. Whereas for all concretes having an air content more than about 4%, the durability factor is very high. So what we would like to do as far as specifying the concrete is concerned is to have concrete which has at least 4% air in order that the concrete is durable under freezing and thawing. So this determination of durability factor is at the root of our exercise to ensure durable construction. So with this, we are coming to a close to our discussion today. We set out to discuss the properties of fresh concrete and the properties of hardened concrete in terms of strength and durability, and that is what we have accomplished. Here are some of the textbooks or reference materials which you could use to get information and also try to do the questions that we posed in the lectures. Thank you.